Every cyclohexane exam has one question where you're asked to compare two chair structures and pick the most stable one. And sometimes they look almost the same. Today, we'll lock in how to choose the most stable one every time. Hey there, ninjas. In this video, we're going to learn how to rank cyclohexane chair conformations by relative stability. This isn't a video about how to draw chair structures or how to flip them into their chair flip conformations, just how to decide which one is more stable and lower in energy. But I do have links to all those other videos that I'll link to down below. By the end, you'll have a short checklist that you can run through on the exam without panic. Let's start right away with the most important idea. Equatorial groups are more stable than axial groups. Why? When a substituent is axial, it sterically clashes with the other axial groups around the cyclohexane ring. And that steric interaction raises the overall energy of the molecule. When that same group is equatorial, it's further away from the other substituents, making it lower in overall energy. Less crowding, more stable. So if a molecule only has one substituent, the choice is easy. Put that group equatorial. What happens when there's more than one substituent? Now things get interesting. With multiple substituents around a chair structure, you often can't get all of them to be equatorial at the same time. So we switch from perfection to prioritization. Since the equatorial orientation is the more stable position for a substituent, the most stable overall chair is going to maximize the number of equatorial groups. So this is your default move. Count the number of equatorial groups. More groups equatorial equals the more stable chair conformation. But what if two chair structures have the same number of axial and equatorial groups? Sometimes, if the same kinds of groups are equatorial in both chair structures, the structures may just be equivalent in energy. That's an okay situation to be in. Neither chair structure is more stable or less stable relative to the other, and they're degenerate, same energy. But we can ask a more sophisticated question. Which kinds of groups can tolerate being axial better than others? Here's the hierarchy. By far, the winner is the hydrogen atom. It's the smallest, so if we have to put anything axial, we prefer to put the hydrogen group axial. In second place would be heteroatom-based substituents. If the carbon is directly attached to an oxygen or a chlorine or a nitrogen or a bromine, the group can orient so the lone pairs are pointed into the center of the cyclohexane ring, and those are less sterically clashing than actual carbon chains. And then, if we have to, carbon chains are the third most stable group to be axial. At least with most axial groups, you can orient the axial group so two hydrogens are pointing towards the center rather than an entire extra carbon chain. Again, if two chair structures have the same kinds of substituents and they have the same number of axial and equatorial groups, then they're just going to be the same energy, and that's okay. But if we're in a situation where we can prioritize, the group with the heteroatom is going to be more stable if that heteroatom has to be axial. Lastly, let's look at one substituent that might surprise you. If your cyclohexane chair has a T-butyl group as one of the substituents, that T-butyl group is absolutely blocked from being ever in the axial position. With the T-butyl group in the axial position, one of those methyl groups has to stick directly into the center of the ring, and that will severely clash with the other axial hydrogens around the ring. That steric clash is so great that it blocks the T-butyl group from being in the axial position. So if you have a cyclohexane chair with the T-butyl group, the orientation with the T-butyl group equatorial will automatically be more stable, even if that means there are more overall axial groups. The axial T-butyl is so high energy that it prefers to be equatorial in just about every circumstance. So here's your full decision-making process. Count the overall number of equatorial groups. The more equatorial group structure will win. If both molecules have the same number of equatorial groups, they may really just be the same energy. But if we have to, we can prioritize putting a heteroatom group in the axial position, and that will be more stable than an alkyl group. And finally, the T-butyl group must be equatorial, even if that means more groups end up being axial. And that's it. If cyclohexane chair conformations have felt overwhelming as you're just getting started, that's normal. There's a lot of visual noise, but stability questions are actually quite systematic, once you know what you're looking for. Next, you should really lock in going back and forth between chair conformations, and I have a link to that video down below. You've got this, and now you've got a method to back it up.
Thanks for watching. If you like what you saw today, maybe let your instructor know about these videos, or your friends at other schools. Check out some of these other videos and playlists, see what you like. As always, don't forget to like and subscribe.